Hi there, welcome to this video. A while back, I created a project to look at Unity.Mathematics, look at noise and how they've got a bunch of noise functions in the mathematics library. And can we use this to basically make objects move in a scene in using the job system so that it can scale in a pretty large way. Noise is cool in 3D for a bunch of reasons. You can use it to generate height maps and make interesting terrain. So imagine procedural terrain generation using noise. Okay, so having a look at different noise functions and seeing what kind of output they create can give you an idea what kind of terrains you can create and how you might tweak those. So you'll find this project on GitHub. GitHub. Sorry, thought I was saying something wrong there. So it's wasmo/NoiseMoveDemo. If you look for that, you'll probably find it. And if you see this, then you have found it. Code, so instead of using scripts, C# isn't really a scripting language, so it's not scripts, it's code. So all the actual code is in here. Basically, we can download it as a zip file. So using HTTPS here, we can download it as a zip file, and that's what we'll do. And we'll go from there. Okay, now I'll go to Unity and make a new project. And I'll use the latest editor. I'll probably use the URP. It'd be nice if I could turn off all the extra template stuff. Anyhow, noise demo video. All right, so the import's finished. Let's get rid of the junk, shall we say. I'll need to make a new scene. Hey, come back. And we will get rid of all the example assets. Keep the presets. Why not? Materials. Why not? Scenes. Okay, so here we'll save. What do we call this thing? Right. Yes, creative noise demo. Okay, we'll get rid of the other stuff. Let's see. Scripts. Well, we know I don't like scripts, settings, and tutorial. Okay, we'll get rid of that nonsense. And we'll get rid of the README bizzo. All right. Now we have a URP project. Now the other thing we'll need is not this. We'll need to not in project registry. We need the burst compiler. So give me the latest burst. All right, cool. Now back to the inspector. So let's get the code and bring it into the project. Where did I pop it? I popped it in. Yeah. There, by type zip, where I hold on. Really? Compressed file. Yes, of course. Okay, we'll open that there. Now, can I open this in Explorer? Lovely. Back to this one. Okay, we'll just take the code and the license and the README. Done. Okay. So let's have a look at the code just quickly. So what do we have? So I have an enum here for the different kinds of noise. Some things didn't work so very well. So these are the ones that worked, that didn't make it either crash or just freeze, lock up for some reason. So there were a couple, and p-noise was one that kind of just made things freeze. Probably I'm using it wrong, but given there's very little documentation, what are you going to do? What else do we have here? So there's the controller, which is a MonoBehaviour. And I use the add component menu trick to make it easy to find and add through the inspector. What else? We'll see here that the kind of noise, that enum I was just looking at before. This is how you can choose which noise function you want. So the point being that we can change the noise function and visualize it basically, see what it looks like. Here we can set up prefabs. There's some settings like the rows and columns in terms of, it's going to be a grid, right? So we'll have a two-dimensional as if you look down, it's sort of just a grid, and the idea that they can move in the in the y direction. They vary in height. They wiggle that way, basically, make it interesting. So think of it as a dynamic height map if you want. Let's see, this, yeah, anyway, so this is more about scaling, and this is the number of objects. Let's see, so we have basically a routine to create instances. So take our prefabs, make instances, pop them into an array. We're then positioning them in the scene, and then we're creating a transform array which is used in a job to manipulate their positions according to the new heights that are calculated. That's it. We have therefore a noise function, a noise position job, which should be varying just the height. It's been a little while since I looked at this code. So now, as I like to do, we have a begin function that knows how to schedule this job. It has internal knowledge, so it knows how to do that, how to schedule it right based on what kind of job it is. So this one is an iJob parallel 4. Let's see. So it's going to set it up with the parameters needed. So you'll have the current positions, the parameters of the, so this is the parameters from the controller. Parameters being these size params. Okay. Think of it as your simulation parameters, the parameters for the overall simulation. What else? So then basically it's going to schedule the job with that length, and away we go. And then you can see here the actual execute function, which is where the work is done in the job, in the background thread. Really, we're calling a utility function that makes a position given the index, the time, the size, and the noise function that's chosen. So, which also, the nice thing about this is it means the noise function, we can vary it from frame to frame and see the noise change from one to another. So again, trying to increase that utility as just a noise visualization tool. All right, what else do we have? The scene update, which should use the transform array. Yes. What this will do is basically just take the position and update it into the transforms for all the objects using a background job. So that's straightforward, super straightforward stuff. So that's really it. The main work there is dead simple, and a lot of the magic's actually happening here in these utility functions. So yeah, we can go through that super quick. So first, a few things that are worth noting, by the way. Now, this is just a static class. So it's not a job, right? But we can still use the burst compiler, and it will still make a difference. One of the key things, of course, is we're using value types, and we're using the mathematics types here, which means we get the benefits of the burst compiler and what it will do with SIMD instructions. So that's cool. It's very cool. We can even use these within. So for instance, if we look at the controller, which is a MonoBehaviour, in here I think it uses the make position in setting up the positions in the first place. Maybe I'm lying. I have a feeling I'm using at least one of these burst compiled tasks within the, I know I've done it before anyway, where a burst compiled task can be used from a MonoBehaviour. So you still get performance improvements using burst compiler. With static functions and using the mathematics library. Okay, so what are these things doing here? So making a position, this is the one that's called from the job, the one that moves the position using noise. So here, what are we basically doing? Obviously, I'm trying to generalize the way the inputs into the noise function, because the noise functions are a little bit different. If you want to see the documentation for the noise functions, if we go back to Unity, give me a second. From the package manager for mathematics, actually, if I go to, yeah, that's not what I want. If I go to in project, okay. Oh, that's always fun. Oh, man. Where is it gone? Packages. Mathematics is here. Okay, the annoyance is that typically from here is where you find the documentation. So the fact that I can't click on it in the package manager is super annoying. Not helpful, guys. Not helpful. Oh, right. Okay, well that might at least lead us to some documentation we can find. Okay. And doc. Pseudo random note. Oh, that could actually be useful. Okay. Well, given how tricky it was to get to that, I'll put that in the description link. Let me make a note. Okay. Actually, while I'm there, I'll put this in there too. Okay, back to the code. Get rid of that. Now, so what are we doing? Right, so we have our make position. This is figuring out, okay, so the whole idea is I've just got a two-dimensional array, and given the number of objects per row and the number of rows, we can kind of figure out where in a single linear array any object should be in an XY or a row column coordinate. That's what this is doing. So we have, you know, for a given index, so this is because it's processing everything from start to finish in the array, it's trying to figure out, well, it's going backwards from, you know, so if, let's say there's 3 by 4, okay, so the linear array length will be 12. So if we have 3 rows with 4 columns, then the whole idea is if I know the number per row, right, which is if it's 4 columns, that's 4, right, there's 4 in a row and there's 3 rows. So then I can use that to figure out the row and column given any position between 0 and 11, right, 12 positions. So given that, I can figure out an XY position. Then from that, we can say, well, where, you know, let's apply that to the noise function, whatever the noise function happens to be. So then, and then we're letting it vary over time, right? So that's why we need to get an XY position, we need time, and then we need to know which noise function we're applying. From that, we get the height, and that gives us a new, you know, float 3, which is, you know, XYZ float value. So we're using the XY part, the height, and the XY, sorry, the X part of the XY pos and the Y part. So this is meaning thinking in terms of row and column X and Y. So obviously if we take a 2D grid, right, of row and column, and we lay that flat, and then we have height being, you know, the noise function, then we have a, you know, a plane that can wriggle vertically. That's why it's like this. Okay, terrific. Noise function. So given whichever enumerated type the noise function, you know, given which value we get, it's going to call the appropriate noise function type. So these functions are part of Unity.Mathematics. So we have C noise, PSR noise, PSRD noise, and you can actually, and I did actually, you can Google these names and they will roughly find a description of that noise function, not from Unity's documentation because there isn't really much of that, just from general mathematics about these algorithms. They're fairly standard algorithms for the most part. You have to guess a little bit sometimes. Anyway, that is exactly which algorithm is being applied, given the name, how short the name is. That's where the guesswork's required. Okay, so what I've done here is I've mapped, so this is C noise, as you see up here, and then I'm calling noise.cnoise. So this is the actual name from Unity.Mathematics. Noise being that's the public static class. And if I, let's see, I should be able to open that up. When my brain kicks in, let's go there. Go to definition. Here we go. All right, well, anyway, so you can see here, that's essentially what the, you know, you've got the noise class, lowercase n, not very C# naming convention compliant. With function name, again, lowercase, not very C# naming convention compliant, but who cares? Then, okay, so we've got our different noise functions. P-noise I'm not using because it made things lock up and freeze. I don't know why exactly, which really means I didn't spend enough time to get to the bottom of it. But I had enough working examples that it was worth just moving ahead. Okay, so that's pretty straightforward. That's really all this is doing. It's given the type, or rather the enumerated value of the selection of the noise function. It's calling my wrapper. So this is my wrapper here, and it's adapting. These wrappers try to adapt for the differences between the given noise functions so that they have a common signature, method signature, so that I can call it from up here regardless. That's why I've got this wrapper function. Okay, that's why I made these wrappers. And that's it. That's really all there is to this whole thing. So let's now make use of it. Let's put it into action. Over to Unity. Alrighty, so in the inspector, all right, let's add our let's create an empty. This will be for our controller. So we'll call this NoiseRoller, maybe with an R. Let's add our component, and down here we should have noise move demo. Add that. Terrific. So this is where we can configure it, and by default it'll be a 10 by 10. Let's make a prefab, because without that it's going to get really boring. So just collapse that thing. Up here we'll nope. Let's make a prefab folder. Prefabs. Okay, let's make that prefab. So now obviously this could be any 3D object. Ragdoll could be fun. Imagine a ragdoll moving up and down. Things wiggling around. Okay, I'm going to use sphere. Let's also make a material for the sphere. Material. Now this is where it gets a little bit interesting. You know, when you're doing, if we have lots of objects, then the choices we make here about this material will impact rendering time. Okay, so if this is lit, you know, actually, look, I'm going to go for unlit. I'm going to do that for a couple of reasons, but part of it is because it's simpler, but it'll also perform better. So look, I will make a GPU instance. No, that's going to change a lot. Let's go with a bright green, super visible. Yeah, that will all do. That's fine. Okay, so we have our name. This is our green, bright green, actually. We'll throw this onto our sphere. What will now be bright green. And we will change this to be green ball, because that's what it is. And we'll pop that into the prefabs. Now, before I get too carried away, position, you're right, is 0. Yep, good. So we'll get rid of this. Now we go back to our controller and drag our prefab into here. Save our scene and, well, actually, first of all, no, that's in 0. Okay, great. Just thinking what's the position, just in case it's like miles away. Now, the other thing I should do is, where's the camera and is it facing it? Yes, okay, it is. Let's hit play and see what happens. There we go. Green balls. Moving according to P noise, I think it was, by default. C noise. Okay, so let's choose one or the other. Okay. Not doing a great deal of much. S noise. So as you can see, yeah, that's cool. We can play around with our different noises. We can choose the noise function. Okay, wait. What? Why doesn't? Hang on. Oh, because I'm dragging the noise controller around. That's not going to change a great deal. Sorry, I thought I was moving the camera around. So just trying to find a good. So alternatively, I could move the actual position of the noise, but let's make it. So if it's 8 minus 1 minus 10, that's fine. All right, that gives us something. 8 minus 1 minus 10. All right, let's make that 8 minus 1 minus 10. Make that the scene. Now the fun part is, yeah, okay, so let's just hit that. So that's a nice gradual thing. Let's try changing the row height. Yes, okay. So this will spread it out a bit. And we can obviously make it 0.5 and make it a bit more compressed. So it just looks continuous. We can also, change the size of this thing. We can see we're getting some insane frame rates, but that's basically because we're not doing much. So if we make this 200 by 100, which is 20,000 objects, what does that look like? More modest frame rate of 46 frames per second. A pretty big sea of stuff, wiggling at a reasonable rate there. And again, if we make this 0.5 by 0.5, it looks like a continuous motion of algae or something. But there we are. And obviously if we'd used different shaders where you had lighting effects, it would probably make the video card work a little harder, but you'd actually be able to distinguish from one of these wriggling balls to the other. The other thing is there's a bunch of things we can actually do to optimize this. For instance, because we'll find the rendering time will be impacted by how many things are actually visible on the scene at once. So you can actually shorten the view frustum so that you could see this as a procedurally generated scene, and we can see that this view frustum is actually containing all of the objects. So if we shorten that up, so for instance, imagine a flight simulation, or you've got a plane, it's going over a field of objects. You can actually have it so that time isn't varying, so they look still, but as you move position, that's varying. And then you could make it that as the plane moves, they come into the scene, and by shortening the view frustum, you can actually make it possible to have even more objects in the actual scene, but because only a subset of them are being rendered, it'll perform pretty well. So there you are. That's a very quick overview of the code and how to get this project and basically try it out for yourself. Hope you enjoyed this. If you did, it would be super great if you could, hit the like button. Feel free to share it with other people who might be interested in looking at Unity's noise functions that are in the mathematics library, who might be interested in the job system, or who might be interested in procedural generation of things. So, feel free to share. If you haven't subscribed, by all means do so. There's plenty of other material in the channel about the C# job system and how to make good use of it. Thank you for watching.